All right, welcome to the Artist Forum again. Welcome to another video on, I wanted to do a video on audio units, explaining them, sort of giving the musical artist an idea of what a lot of, especially, music producers, audio engineers, recording engineers, mixing engineers, mastering engineers, what sort of their language is and what they talk about on a daily basis, and that is these audio units, and just really want to, help artists develop a foundation that they can learn. And a lot of people who watching this video might a lot of artists might start asking, especially musical artists, start asking, why do I need to watch a video on these audio units? If I'm a vocalist, why do I need to know what dBFS is or dBV? And what I would say to those artists is, you really, if you're in the studio or you want to be a vocalist who starts to produce their own tracks and starts releasing their own material, you're gonna need to know this language, especially when you're in the studio and you're working with, your audio engineer, recording engineer, mixers and mastering engineers. You're gonna hear these terms every now and then, and if you can learn this language and you can start to talk their language, you can start to communicate better with your creative team. So I don't want to take a lot of time here in this introduction, but I think it's crucial. And with this channel, I wanted to start really building a nice foundation for a lot of, especially musical artists, can understand and build from. So with that said, let's get in the video. All right, now, before we start talking about like these units that are in dB and dBV, dBFS, it's really crucial for us to talk about what logarithms are. Now, I'm going to put links in the video where you can skip, and sort of like a table of contents for this video, so you can kind of know where to go in this and refresh yourself. I want these videos, especially these beginning videos, to really be sort of a reference for everyone, so you can go back and re-watch them and think about what's going on. So to move forward, I want to just quickly discuss logarithms, what they are, where they came from, and that'll necessarily help us move into explaining these units and what's going on. So I want to first discuss what logarithms are. Real quickly, back in about the 1500s, mathematicians and scientists were having difficulty trying to multiply difficult large numbers and difficult numbers. And so people like this John Napier and Joost Burgi, they started developing ways of making these multiplications easier. So what they proposed is they started creating tables, logarithmic tables. And I want to do a quick example here of, say we have a number that is of a base 3 to the exponent of 1, 3 to the exponent of 2. This is an easy example, and I'll go into a more difficult example later, but say I want to multiply 59,049 times 14,340,907. Well, I chose those numbers in the base 3 table, but if I want to multiply those two numbers together, what I do is I go to my base 3 logarithmic table, and I find the first number, and I find its corresponding exponent. So 3 to the 10 is 59,049. Then what I do is I find the second number in the table, I find its corresponding exponent, and then what I do is I add the exponents together, which is 25. Now, what I do there is I go to 25 on my logarithmic table on the left, or what John Napier and Joost Burgi did is they called them the red numbers, or the logs, which are basically the exponents. And what you do is you go to the 25th column, and that's your answer. You look over on the right and notice that that's the answer to the multiplication. But what you really should take from this is that we took a multiplication equation and we basically just turned into addition and using the table. So granted, that example, I used two numbers that fit in this base 3 table, but what if I have numbers like this, or like, this? Well, what John Napier and Josberg did is they really created tables that had base of 1.0001 or scales of that, so they can start to really quickly multiply difficult numbers. So again, you just do the same properties. And now imagine if I wanted to multiply 4.135 times 2.345, obviously you have to go really far down on the table, like say the 18,000th column or something. And notice that this takes a lot of computation time. But in essence, that's what they did back then. So with this example, I did a pretty simple one again, but again, you find the first number, and you go to the corresponding exponent is 5. You go to the second number, and you find its corresponding exponent. Again, you just add the exponents, which is 18, and then that's your answer. All right, so I just want to summarize what we discussed with logarithms, and one question that might arise here is, today with calculators and what we had to deal with in math class, someone might ask, well, if I have to compute these logarithms and I'm just turning this multiplication into an addition equation, but I have to compute the logarithm, wouldn't it just be easier just to multiply, just go through the multiplication equation? And really the answer is no. Even back in the day when they didn't have calculators, imagine if they had to multiply these numbers and one person had the same numbers and they had to multiply it. Well, you're just having to reinvent the wheel all the time. And large numbers, a lot of people would come in, especially in the science, they would typically come across these same large numbers. And if you have to continuously compute them, it's just, again, reinventing the wheel. So by having these logarithmic tables, by going through the brute force of creating these tables, you're creating, let's say, like a calculator encyclopedia, where instead of having to go through and reinvent the wheel and keep multiplying these numbers over and over and over again, you just use this table now and look up your numbers and you just add and you find your answer. So logarithms, basically, by taking this complicated multiplication equation and just turning into addition by using logarithms, we're just taking the log of the first number and the log base of the second number equals the log base of the answer, but we've turned from multiplication into addition. It makes things a little more simpler, especially when we're dealing with these units that we're going to discuss later on, and gain structures of levels, where now all we have to really do is we just have to add or subtract numbers. Say I have a plus 2 dBu signal, and I'm like half the power now through a pad or something, or let's say a plus 20 dB of a gain structure. All I do is I just add 20 dB to that. So plus 2 dBu through 20 dB of gain, I'm at 22 dBu now. It's pretty simple. You don't have to, divide by 2 if you're having the power or whatever, or having the voltage, you go down 6 dB. So it just makes it easier. Also, just to discuss what we're going to go in the next section, using these logarithms, our ear, it helps us to perceive how we actually hear. How we actually hear is more on a logarithmic scale, so it sort of more closer reflects how we actually perceive sound by dealing with logarithms, and I'll discuss what that means in the next section. So also another reason why we need to talk about and understand logarithms is the fact that our ear and how we hear, our ear is not a linear mechanism. It reacts more on like a logarithmic scale, and I will show you sort of what I mean and show you an example so you can better understand what I'm saying by this. But our ear is not linear at all. We hear on such a wide range of numbers that that's what a logarithmic scale and why we plot on a logarithmic scale is for, is to plot numbers in such a wide range. Well, our ear, that's also how we perceive sound, is really more logarithmically, and I'll show you what I mean by this. So here we have sound intensity levels, and this is like a wattage per meter squared unit, and you don't really need to understand exactly what this is, but just understand that, you know, when the threshold of hearing, what we can just barely make out, that's 0.0000001 watts per meter squared of sound intensity. Now, just, you don't need to understand what sound intensity is, you know, like a power per meter per square meter of a sound wave. But what you should really just take out of this is that, notice from like the threshold of pain to the threshold of hearing, that's really like an order of magnitude of 1 trillion to 1. That's just an incredible range of what we can hear. Now, if I go and I plot this, and I plot these sound intensities, as you notice on the y-axis, it's a linear scale. So as you see on the x-axis, you know, each, you know, threshold of hearing, Russell leaves up to a race car, and then I plot those intensities on a linear scale on the y-axis. As you see this, that's not really how our ear perceives this range of intensities. And because you know, when we go from like threshold of pain to a typical rock concert to like a subway or a loud city, you know, you notice these drastic changes, and even everything else is just so small. That's not really how we hear, and I'll show you what I'm talking about. So even if we zoom in and take out the jet engine and just zoom into like the race car down to like threshold of hearing, you can still start to make out more what's going on, but that's still not how we perceive the sound. So if we plot these sound intensities on a logarithmic scale, this is going to be more reflective of how our ear perceives this spectrum of sound intensities. So now as you see this is more typically how we hear. If you go from like threshold of pain to a typical rock concert down to like threshold of hearing, you see how that's more along the lines of how we hear. From like the threshold of pain to a typical rock concert, yeah, the threshold of pain is very loud, but then when we go to a rock concert, it's a little bit quieter. Then to a subway, it's a little bit more quieter. Then from a subway to a loud city street, it's just even a little more quieter. It's not like when you go back on a linear scale, how there's just drastic change and then everything's kind of the same-ish. You know, it's just not how we hear. So our ear perceives this wide magnitude spectrum of sound intensities logarithmically. And that's really what you should take out of this. Now, also real quickly, why I want to show understanding of logarithms and logarithmic scales, the importance of it in audio and audio engineering, what we do. If you look at this DAW of, you know, video of this EQ and how it's plotted on the x-axis, the frequencies are plotted on a logarithmic scale. I'm going to show you sort of more why we do that. Now, if I take that EQ curve and I plot it and put it into Excel, and you can sort of see the EQ curve is sort of what I had set up there in that EQ in my DAW. It's on a logarithmic scale. You see, notice the frequency axis, the x-axis is on a logarithmic scale. But what happens if I change that scale to a linear scale? What sort of happens here? So when I do that, what happens is that, as you notice, a lot of the low to low mid frequency information sort of gets cluttered and crammed on the left part of the graph. It just gets harder to see and really have a good view of our audible spectrum from 20 hertz to 20,000 hertz. So a lot of the reason why we plot our EQ curves and you see them on the logarithmic axis is because of that. It's just easier to see, you know, our audio spectrum better. And also to take out of this is that frequency also plays a big role. in, whether it's the lows, mids, or high of how we perceive the sound. And this is a whole subject for another video, but, the Fletcher-Munson curves. And really, what level, what dB SPL, what sound pressure levels are you mixing down at, whether you're mixing down a really high level, a decent level, or a quieter level, you're gonna perceive the lower frequency information, the mid frequency information, the high frequency information differently. So one sort of secret that mix engineers do to really get to that level is to really to mix at a consistent level. Find a consistent level that you're really good at, that your environment at, and mix on that level to really get the timbre to really get the tonal balance of your mix, and know that when you translate it to other speakers or other environments, you're going to be comfortable with that. So get comfortable with a certain mix level, because frequency plays a big change and a big role in how we perceive sound as well. So also take that into account and note. All right, so now let's really get into what decibels are and Bels, and just discuss where we can start to now derive these units. Now, a Bel was derived from the telephone industry, and we can get into the history of that, but it was really a unit to measure gains and losses of the telephone line, and it went from miles of standard cable to later the telephone company adopted the Bels unit to discuss the loss or the gain, most of the loss of a telephone cable. Now, major thing you really should take out of this is that we're really dealing with ratios or changes of a quantity when we're dealing with these units. So when we talk about a change of quantity in Bels, we're doing the log base 10 now. Remember those bases of like 3 or 1.001? Well, what we're using is like the common log, a base 10 number, log to the base 10 of a quantity 1 over quantity, our initial, or the Q naught is our initial or our reference quantity. And that's what we call a Bel, or a change or ratio of powers. If we want to talk about the power now of a quantity, W1 is the where we're at now in our wattage to our initial reference in Bels. Now, a decibel is a tenth of a Bel, and the decibels were more adopted for finer resolution. And again, to put that change or ratio of powers in decibels, we just do 10 times the log base 10 of where we're at now in our wattage to our reference or initial wattage. The first unit we can talk about is dBu, which the U stands for unloaded. And when we dealt with a lot of this stuff, back then, there was an impedance associated with the certain line, like the telephone line or whatever, and a lot of times we sort of started to have a lot higher impedances, especially with op amps and other things where it's just almost a high impedance. So a lot of times we just use this unloaded term. You don't need to get too much into that, but typically they're used for studio audio or professional equipment, and the reference is 0.775 volt RMS, and RMS stands for the root mean square. It's just an average of the waveform in a way, and I'll sort of show you an example as we go on. But one thing you also should understand is, since this is a volt reference, we need to understand that the power is proportional to volts squared. So when we go through this, instead of using 10 log base 10 when we're dealing with voltage units, we need to do 20 log base 10, and you can see why in this equation. So 0 dBu would be like 20 log base 10 of 0.775 volts RMS to 0.775 volts for RMS. What would be really good to understand here is that when you have a sinusoid, audio. Let's say this is this would basically be a 2-volt peak-to-peak audio, let's say sinusoidal waveform. Well, the peak of that is half of the volt peak-to-peak quantity, and then to get the root mean square, the sort of average of that, you take 1 over the root 2 of the peak of it, and you'd get 0.707 volt RMS. So that's sort of what RMS means and how we derive that. dBV, sort of like we said, now we're dealing with voltages. First, it's typically using consumer equipment like CD players. It's more considered consumer level. Its reference would be 1 volt peak. So 0 dBV would be 20 log base 10 of 1 volt peak over 1 volt peak. dBFS is a little bit more complicated of a unit to explain. Just bear with me here. When we were discussing dBu and dBV, we were sort of in the analog continuous domain. We were measuring a analog, let's say, voltage, a signal, say in a preamp or something, But when we're dealing with dBFS now, we're in our computer, we're in our DAW, and this measurement really is where it comes in. So basically, dBFS, where FS stands for the full scale value. The full scale value is the full scale digital bit word that you can represent, such as like 1, 1, 1, 1, 1, 1, 1 here in this picture, this graph. So 0 dBFS would basically be 20 log base 10 of whatever that full scale digital bit word is over the reference, which is the full scale digital bit word. Now, minus 6 dBFS would basically be, let's say, half of that full scale voltage. So if that full scale voltage was like 1 volt peak, it would be 0.5 volt peak. We'd be minus 6 dBFS down. Now, you should also sort of understand that when we're in the digital realm in our DAW, we have, our master bus meter, we have peak meters, and we have RMS meters. And really, the digital meter, you can view a lot of different meters, but a lot of the peak is going to be really that digital waveform instantaneously. You can also look here, as you see, the RMS max meters as well. So I really want to just clarify though and make sure it's understood that this, when you're in your DAW, there's an incredible dynamic range that you have, and we can get into that later, where if it's 32-bit floating point, there's an incredible dynamic range that you have to really deal with these signals, and that's a whole nother video. But really, to understand the importance of making sure when you mix and you master, you're not clipping digitally, you're not going, a lot of your signals in going above the full scale 11111 value it's mostly because for your converters, your ADCs, your analog to digital converters, your DACs, your digital to analog converters. It's really most important there because digital clipping really is sonically unpleasing. Other units like dBm and dBW, dBm is typically not used in audio because it's such a smaller value of reference to a milliwatt, and a lot of times when we're dealing with loudspeakers, we're dealing with more watts. So real quick though, a dBm is referenced to 1 milliwatt. So 0 dBm would be 10 log base 10 of 1 milliwatt over 1 milliwatt. Now, if you have the power, it's 3, you go down 3 dB. But notice if you half the voltage, you go down 6 dB difference. And I really want to stress one thing here, that when you are talking about gains and losses, you're really talking in terms of dB value. You don't say, yeah, the gain of this amplifier is 20 dBW. You say the gain of this amplifier is 20 dB. Now the output could be dBW, and the input for the specification could be dBW, but you don't typically say that this power amplifier has a gain of 20 dBW, you just say 20 dB. So I really want to make that distinction here. Now, sound pressure levels are typically used more in audio recording discussions. Now, the reference is basically the reference pressure is the threshold of hearing that we discussed in intensities, but it's in terms of newtons per meter squared or pascals, and not in terms of the intensity, which we discussed, which was in watts per meter squared. But similar to all the other units, minus 0 dB SPL would be 20 log base 10 of 0.0002 pascals over the same number. But one point to notice in this is that, we're back in terms of 20 log base 10 like we were in voltages. So just know that power is proportional to pressure squared or voltage squared. So whenever you're dealing with pressure or voltage, you need to sort of be in the 20 log base 10 calculation, as opposed to when you're in power where you're sort of in the 10 log base 10. All right, so the VU, or volume unit meter, basically a lot of you will come across it and plug-in analog emulations of older pieces of equipment, or even the actual older pieces of equipment. A lot of them have VU meters on them. A point to note about the VU meter is that the needle, the actual needle in there, and how it moves, and the actual mechanism for it to move, it had a rise time, which a rise time is basically how fast that needle can move. And really the rise time definition is, I would say, how fast this 300 milliseconds can it go from, say, 0 all the way to 100% of its value or whatever. So in a way, that was sort of the rise time, and for this VU meter it was roughly 300 milliseconds. So what that really did is that, in a way, averages out the signal. You're not seeing instantaneous peak values like a digital peak meter would be reading. So you're really seeing more of the average RMS of your signal. And typically 0 VU would be really equated to about 1.228 volt RMS, or plus 4 dBu. That's sort of what, if we input a 1.228 volt RMS continuous wave sinusoidal signal, we want to see, we'll calibrate out our meters so it reads 0 VU. Now also to know with the VU meter is that the 0 on the VU meter isn't the maximum headroom. There is still headroom above that. There is roughly 18 to 22 dB of headroom above that, and this was more on the analog, like console or the analog, equipment. Your average signal, you wanted to be around 0, and your 18 to 22 dB of headroom was really to take into account any of the transients, anything that was not it does add to the average signal, but it's more of the quicker part of the signal that the VU needle doesn't register. So just know that, if you start to go above 18 to 22 dB of this headroom, and you start getting into bigger transients, or you start pushing your signal, you will start to get into analog distortion, and that's a whole nother video talking about harmonic distortions, and we can get into that. But another question about this VU meter is that, what would 0 VU on my VU meter equate to, on my dBFS DAWs digital master bus meter? What is that? And I'll discuss that in here in the next section. All right, so the question that sort of arises now is what 0 VU, or what VU number equals what dBFS number equals what dBu number, dBV, and how do we, where's like a commonality here, I guess you can say. And the way to answer that is what was sort of done back in the day, and even now, when you're dealing with consoles and you're going into your digital recorder, is you would input a 1.228 volt RMS continuous wave sinusoidal signal. So that's the average of the value that would read 0 VU on your VU meter. And then what you do is you'd basically adjust the trim before you got into your digital recorder so that it read between -12 to -20 dBFS. Typically, they would sort of choose -16 to -18 dBFS, and I'm showing roughly -18 dBFS here. I also want to state that I'm not 100% sure, but because in the digital realm, you have digital peak meters that are very good at reading the instantaneous peak as opposed to what the VU meter could read. I'm fairly confident they were adjusting the trim until it read -18 on the peak meter rather than the digital RMS. But still, anyway, the biggest point to take out of this is that you have all this headroom that I discussed before in the last section. You have roughly 16 to 20 dB of this headroom for transients or the peaks. Now from all this, basically it just boils down to, let's say 1.228 volt RMS or +4 dBu equals 0 VU equals -18 dBFS. But it was a calibration. You could 0 VU and everything on the left could equal -12 or -22. It was just really how you adjusted things. All right, so in closing, I would just like to summarize and say that these decibels, these logarithms, and expressing the ratio of a quantity to a known reference, it sort of helps us correlate to how we actually hear. And I know this was highly technical, and believe me, I thought a lot about doing a video like this, but honestly, the music industry is so vast, and music producers, mixing engineers, mastering engineers, I mean, this sort of language is their bread and butter. This is what they deal with on a daily basis. And any artist trying to be better at their craft really should, be willing to try to learn this, I would say, almost dialects of this musical language. That there's the songwriting, and then there's the mixing and mastering, and there's certain things that most of these people talk about. And to be an artist, to be able to start to understand more of these areas, you're going to be better off in your art. So please like and subscribe to the channel. Comment below about if there's anything you'd like me to go into further that I didn't really explain, or you'd like to see future content. I'm really here for you to help you be a better artist. And if I appreciate it if you came back and you see what other video content I come out with, but I'm here to help you be a better artist. So I want to thank you again for watching the video, and I'll see you soon.